I'm excited to present our work. It's called Live Image-Based Neurosurgical Guidance and Roadmap Generation using unsupervised embedding. Quickly before I start, I'd like to point out that we will be showing some surgical videos, so some graphic content. So if you do not respond well to that, please be aware. Then to start off, I would like to give the relevant medical background so you have the context to understand why we did what we did. I'm sure you're all aware that minimally invasive surgeries are becoming more and more prevalent. First of all, of course, because they are less invasive, and we're also able to reach deep places inside the body. And especially in the field of neurosurgery, which we're targeting today, you could have a surgery on a particular day and leave the hospital on that same day. Especially if you compare this to an open skull surgery, of course, the comfort of the patient is drastically increased. These surgeries are often performed with endoscopes. These are cameras that go inside the body, and they can give you a really unique view. However, interpreting that the video feedback is not that straightforward. There are a few things that contribute to making it quite challenging. So, for example, you have a very limited field of view, and you have low contrast and very similar textures. During the surgery, you can have bleeding and flushing. And overall, this makes the identification of the anatomy and orientation very challenging. I'd like to show you some surgical videos now. And I would like to invite you to try to differentiate between different anatomical structures. I think that you will quickly realize that this is not an easy task, right? Everything is reddish, everything looks the same basically, and there are no distinct, let's say, shapes or borders between the different anatomical structures. So this makes orientation during the surgery very hard to know where you are basically. And of course, there are some solutions to the problems I just introduced. The most commonly used one is called neuronavigation. This is a technique that relies on MRI images that are taken before the surgery. And while this provides very relevant information in quite a high resolution as we're used to from MRI images, there's, let's say, one major drawback, and that is that it relies on preoperative images. So that means that any changes that happen, you cannot see these in these images. And for example, there's a phenomenon called brain shift. This describes how the brain changes as soon as you open the skull, because there's a change of pressure. Or even if you already from a sitting position, you go to a laying position, the brain changes as well. And these, even more if we do any incisions or we remove any tissue during the surgery, this is also not accounted for, and we do not see in the images that we reference, right? So we have surgical tools with markers on them, like here in the animation. These are tracked using a tracking device. And then the location of the tip of the tool is known within the MRI images, and you know what anatomy is around the tip of your tool, basically. But the problem is you are dealing with outdated information. It's not the current situation. And there are a few methods that are able to provide intraoperative support. For example, you could do fluorescence imaging or intraoperative ultrasound or MRI imaging. And these are quite nice. However, they introduce, let's say, extra steps, so they can disrupt surgery, or you need to be an expert in an additional imaging modality. For example, ultrasound works really well, but you really need to be an expert to understand those images. And the MRI images during the surgery disrupt the workflow. So you have 30 or 40 minutes that you just have to wait for that scan to be finished. And together with our collaborators from University Hospital of Zurich, we wanted to see if we could provide an alternative solution that allows us to move away from having to rely on, let's say, additional machinery or expensive machinery. And we defined 3 characteristics that such a solution should have. First of all, it needs to be able to recognize the anatomy live based on what you're seeing, so the endoscope images that the surgeons work with. We wanted to be able to provide, let's say, relative positioning information so that you're aware of your surroundings. And finally, this goes kind of hand in hand with the second point, is the prediction of the anatomy that will come if you would move forward or backwards with the endoscope. And to see if we're able to provide such an alternative solution, we were provided the following data set by the Department of Neurosurgery at the University Hospital in Zurich. And before I talk about data set, I would like to quickly state that we are really privileged to be working with such a data set. I'm sure you're all aware that getting these data sets in the medical field of high quality is extremely challenging. So we're very grateful to have this data set to our proposal. Then the data set itself consists of 166 videos of a specific surgical procedure called transsphenoidal adenomectomy. The surgery is to remove a tissue, a tumor at the pituitary gland, which is located right here. And you can access it through the nose by inserting the endoscope and the surgical tools. Like you can see here, you have to remove some tissue and make incisions here to enter the sphenoid sinus. And finally, once you reach the base of the skull here, you can remove some bony tissue and you will end up at the tumor location. Regarding the data set itself, we have 16 classes labeled with bounding boxes. 15 of those are anatomical structures, and we have 1 surgical instrument class. Overall, we have around 19,000 labeled frames and 3 million video frames in total. And the first thing that we wanted to see was whether state-of-the-art object detection networks work in such an environment. We've seen some similar applications in a similar environment already. So for example, with polyp detection, surgical tool detection, however, extending from this to anatomical detection, it's not that straightforward because, for example, surgical tools look very different from the surroundings, right? Different colors, very distinct edges and shapes. So below you can see the results of the YOLO version 7, which is the network that we use in this case. On the COCO dataset, which is kind of like a baseline, and below you see our results. You can see that the instrument class, for example, works really well, kind of as we expected. And you can see that also a lot of anatomical classes are within the ballpark of that baseline score. And I'd rather show you some videos. I think it's a bit easier to interpret than the numbers. And of course, there's some flickering in the results, but in general, it's really quite stable, even in the bottom video where you see that there's quite a lot going on with flushing and that we're able to detect the anatomy as we hoped. And even though the results are not perfect, I'd like to state that it doesn't really matter for us that we detect, or it's not the most important that we detect the anatomy on every single frame of the video, but more that we don't have any confusion between different anatomical classes. And if we look at the confusion matrix, you can see that this is luckily the case. So if we kind of wrongly detect structure, it means that we just don't detect it. We just don't see it basically, but we see that there's almost no, let's say, confusion between different anatomical classes. So that's quite nice. And if we take a step back and look at the characteristics that we defined before, we can see that we now have live recognition of the anatomy. And the next step would be to provide relative positioning. And since our data set didn't contain any additional information beyond the bounding boxes, we had to come up with something else. And we realized that when we looked at the surgical path, that it's a rather, let's say, one-dimensional path. And if we imagine that we move from, let's say, here, the beginning of the surgery to the final destination, we imagine that everywhere along the surgical path, there's a unique arrangement of the anatomy. So every position should have a certain anatomy positioned in a certain way. So imagine we have this structure on the top here. And since we're in a tunnel-like environment, we expect this structure to grow bigger as we move towards it and kind of move off to the side. Similar for this blue structure here. Imagine this is an opening that we go through, right? We expect it to grow bigger inside as we move forward. Or if we have a different arrangement of anatomy, we'd also expect this to change as we move. And once we can assign these, let's say, anatomical arrangement along the surgical path, we're able to position ourselves. So the goal became to to define a common surgical path by learning the relative arrangement of these anatomical structures. And we opted to do this by using an autoencoder structure. So we have our video frames from the endoscope that the surgeons work with. We use a detection network to get those detections, and we take a sequence of those to provide some context for the network. We feed this to our encoder, which consists of a transformer encoder, and is followed by fully connected layers to reduce the dimension to a one-dimensional latent variable, which is to represent our location along the surgical path. Afterwards, we have two decoders. One predicts the classes and one predicts the bounding boxes. And we do this only for the last frame in our sequence, since we want our position on the surgical path to correspond to our current position, which is the last frame. We optimize this network using the following loss function. So it consists of a cross entropy loss for the classes, and is followed by a bounding box loss, which is an L1 loss, and also conditional, so it's only calculated for the present classes. And I would like to start off by giving you some visual results. So imagine that you travel down this path from shallow to deep. We can now use our model to generate what the model expects to be at a certain location. So which anatomy is present at a certain location, and also its arrangement. And if we look at it, we can see that the structures kind of move in the way that we expected, right? We can see that as we move deeper, the structures grow bigger in size and kind of move off to the sides, like driving, let's say, a car down a tunnel. And for example, the purple structure here is an opening, and you can see that as we move forward, it grows bigger in size. And finally, all right, somehow I can skip the video. But finally, behind, we find different anatomical structures, as if you would open the door to a new room, for example. And there's another way of looking at this. So once again, we have our decoder. It's only the class decoder. And we can generate what classes, so which anatomical structures it expects to be present at a certain location. So in this diagram, on the z-axis, on the x-axis, we have our latent variable z going from 0, the beginning of the surgery, to 1, the end of our surgery. And on the y-axis, we have our anatomical classes right here. And now we let our model predict which anatomy is present at what location. So imagine we take a sequence of our surgery, like the images, and our encoder gives us the value 0.22. We know that these classes should be present there. If we do it for another sequence, let's say around 0.6, we see that these anatomical classes should be present there. So now, based on what we see, we know where we are along the surgical path. Then if we encode the entire surgical video, so we see how we move through our surgical path. So once again, on the x-axis, we have our latent variable, and on the y-axis, we have time. So t equal to 0 means the beginning of the surgery, t equals 1, the end of our surgery. And you can see that in the beginning, we're moving in the shallower regions of our surgical path. Later, we're getting deeper, and later a bit deeper as well. What is interesting to notice that you can see that we spend a considerable amount of time around this area and around this area. And if you reference this to the roadmap that we saw before, you will see that this actually corresponds to the locations where we are making incisions or removing tissue, actually, like in this case. So it makes sense that we spend a lot of time there. I propose that we take a step back to get an overview again. So we start with our video, the video that the surgeons are working with. We use our detection network to get the detections. Later, based on these, we can position ourselves along the surgical path. This allows us to anticipate which structures would appear if we move forward or backward. Now, all of these results that I've been showing so far have been validated by the neurosurgeons, by how they expect the anatomy to appear as they go along surgery. However, we wanted to do like one final check to see if our latent space, our surgical path, actually corresponds to space. So we set up one additional experiment, and it's based on this. So if it represents space, we would expect shallower anatomy to be seen for the first time before we see structures at deeper locations. So imagine you're driving a car down the road, and if everything makes sense spatially, we would expect to see the barn before we would see the factory. And so that's what we checked. We checked the first time a spatial location along our surgical path was encoded. And we can see a nice correlation between time and the first encoding of a location, which means that we actually reach deeper sections later in surgery as we have to work our way through to get there. So that's nice. So this is another confirmation that our latent space corresponds to actual spatial space in a way. Then finally, I'd like to show you something cool that we can do with this method. So on the left side, you see a surgical video, a normal one. You see that we move forward, we move backwards a bit. And all in all, this takes around 1 to 1.5 hours. And on the right side, now since we can assign to every frame a location along our surgical path, we can reorder video. So let's say we discard all the frames where we go backwards and only keep the ones where we're moving forward. So we can see what the surgery kind of looks like if we were only to move forward. So in this part that you see now on the right, we're in the entry of the nose basically. Then we're starting making the incision to get into the sphenoid sinus. It's growing by size as we move on. And finally, once it's big enough, we're able to reach the base of the skull, which is the location where we can access the pituitary gland and start removing the tissue. And so we kind of reduce surgical video from 1.5 hours to let's say 1 minute in only moving forward directions. All right, that is everything that I wanted to show to you today. Finally, I'd like to thank once again the University Hospital of Zurich for providing this amazing data set, and also Leica Microsystems for partially funding the realization of this data set.